You may have heard that space is silent. Sounds can't travel through empty space because it needs a medium like air or water to travel through. So any booming explosions you've heard in science fiction movies aren't really accurate. Maybe you knew that already. But there was a time when space was so densely filled with stuff that sound could travel through it. And that time was right after the Big Bang. Today on our show, what did the Big Bang sound like? How do we know? And what can these sound waves teach us about the early universe? The music of the Big Bang coming up, so stick around.
This episode of Why This Universe is supported by Wondrium. Wondrium offers thousands of video and audio courses on a huge range of topics. I've been listening to Wondrium for years and have enjoyed courses from them on everything from philosophy and history to literature, math, and science. On my queue next from Wondrium is a series of lectures on the modern intellectual tradition. So this is going to cover everything from Descartes and Berkeley and Kant, Hegel, basically the whole canon of modern political philosophy, including some 20th century figures like Wittgenstein and the early positivists and things like this. So I'm really looking forward to listening to this series of lectures. And if you want to learn about this sort of thing or just about anything else, you should give Wondrium a try. You can sign up for Wondrium now through a special URL to get a free month of unlimited access. You can do that by going to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
Today on our show, we're answering the question, what did the Big Bang sound like? But we won't start with the Big Bang, or anything else about cosmology, really. To understand how the Big Bang could even make a sound in space, we need to understand what sound is to a physicist. So sound, like any wave, is really energy passing through a medium. Think of a wave you can see, like water waves at the beach. If you were to zoom in on a water wave, what's really happening is that the water molecules in the ocean move up and down as the wave of energy moves through it. So it's not the water molecules that are moving with the wave. The wave is just the energy moving through the water. Sound is a lot like that, but instead of water molecules moving high and low as the wave passes through them, a sound wave creates regions of higher and lower pressure in the medium it's traversing.
You can think of it this way. There, in between my voice and your ear, where you're hearing the sound, there are regions of high and low pressure, kind of in a alternating sequence, and those move forward through space as they travel through the medium. But this, of course, requires things like air or water or something for the sound waves to propagate through.
So it's not that sound is unique to only air and water. Anytime you have these high and low pressure patterns in any medium, you get sound. But sound will travel differently depending on what that medium is.
So sound propagates through a medium at what we call the speed of sound, fairly obviously. And that depends on the pressure and density of the medium. So sound waves move through air at a different speed than they move through water. And, in some sort of other environment, they can move at a different speed still. In ordinary air at kind of typical pressures and temperatures, sound moves at a speed of about 340 meters per second. And like I said, it could be a little bit different if the space is particularly like high pressure, low pressure, high temperature, low temperature, so on. Humans can hear sound waves in the frequency range between about 20 hertz at the low end and about 20,000 hertz or 20 kilohertz at the high end. And that corresponds to wavelengths between about 17 meters and 1.7 centimeters. It's not a coincidence that this range of sizes is about the size that we make musical instruments out of. My guitar is about, a meter from one end to the other, which puts it squarely in the middle of this wave, a range of audible wavelengths. And most things that we hear, they're roughly in this sort of range of sizes. And again, that's not a coincidence. In a musical instrument, tones are produced by generating what are called standing waves. So random vibrations will tend to cancel themselves out. So if you add a bunch of waves together, the peaks will tend on average to cancel with the troughs of the wave. But standing waves, on the other hand, are arranged in such a way that the peaks add to other peaks and the troughs add to other troughs, kind of reinforcing the intensity of those waves and, strengthening the wave in question.
Think of a guitar string, for example. The string is being held at its two ends by the guitar, making it so that it can only support standing waves that zero out at those two ends. So any wave that does that can be a standing wave on that string. The deepest of these tones will be when the wavelength of the standing wave is twice the length of the string. You get a sort of single hump-looking wave in that case, and it's called the first harmonic. The second harmonic has a hump and a trough, or one full wavelength equal to the length of the string. You get third and fourth harmonics as well, and so on.
And this is true not just on strings, but if you took like an organ pipe or something and looked at the pressure waves going through it, something very similar is the case. This is why musical instruments work. Okay, so that's our Sound 101 tutorial. Now let's talk about the Big Bang. Like we said in the introduction, our universe doesn't really support the propagation of sound waves today. Most of our universe, or most of space, is almost entirely empty. And empty space without a medium, just doesn't allow for pressure waves to propagate. Sound is impossible in vacuum. So despite what you might think from watching Star Wars, and I'm not a hater, I love my Star Wars, there is no actual sound in space. But in the early universe, space wasn't empty at all, right? So the universe was a lot smaller, a lot hotter, and a lot denser. And unlike our universe today, which is pretty clumpy, there are things like, compact stars and in planets and things. In the early universe, it wasn't like that at all. There's pretty much the same amount of stuff everywhere. So there was a medium everywhere that the sound waves could use to propagate through. So sound could easily travel through space shortly after the Big Bang. In particular, the photons and electrons and protons that existed in the first few 100,000 years made up a dense medium whose individual particles were constantly interacting with each other. So just like the molecules of air interact with each other constantly, allowing sound to propagate, the same thing was true among the photons, electrons, and protons in the early universe.
So this dense bath of photons, protons, and electrons made the perfect soup for sound waves to travel through. But still, something needs to create the sound waves in the first place. What was making the sound at the Big Bang?
You might wonder what might have generated sound waves in the era shortly after the Big Bang. I mean, there weren't musical instruments. There weren't, guitar strings or organ pipes or whatever. But the short answer to this question is that sound was generated through the combined effects of gravity and pressure. In the early universe, the density of matter and radiation was almost exactly uniform. It was basically the same everywhere, but there were some regions that were just a little bit higher or lower density than average. And when I say a little bit, I mean about 1 part in 10 to the 5. So pretty much the same everywhere, but there were some places that were 1 part in 10 to the 5 more dense, and other places that were about 1 part in 10 to the 5 less dense than average. So with that in mind, picture some region of space, like a little ball or something, that is a little more dense than average. Since there's more energy, in other words, there's more equivalent of mass in that region, gravity will pull on it and try to compress it, okay? So this region will get pushed together by the effects of gravity, and it will kind of collapse or compress into a smaller volume. But as it does that, the pressure starts to build up in that region as well. If you ever have tried to push on the sides of a balloon and squeeze it into a smaller volume, you see that it resists that, and that's because of the pressure that works against the effects of compression. So what this region will do is the gravity will compress it, causing it to get smaller, but that causes the pressure to build up, which pushes back against the gravity, leading to waves or oscillations of compression and expansion in alternating eras.
So you can think of the sound of the Big Bang as the music of gravity and pressure. These two natural forces working in tandem to create oscillating waves, spreading music around the universe.
So from what we've said so far, you might think that the universe would be just full of a bunch of random sound waves. Every region would have its own frequency and you'd add them together and it would just be a bunch of noise. But it turns out this isn't the case. Instead of just producing random sound or random noise, the early universe itself works kind of like a musical instrument, producing sound waves at particular frequencies or with particular tones. This happens because our universe is constantly expanding. So picture a region, again, in our universe as a little more density than average. If the universe wasn't expanding, this region would gradually start to collapse or compress, just like we talked about a couple minutes ago. But depending on the size of the region in question, the expansion of the universe might prevent this from happening, at least for a while. Right now, our universe is expanding at a rate of about 70,000 kilometers per second for every gigaparsec separating points in space. So 2 points in space separated by 1 gigaparsec. The amount of the space between those 2 points grows at a rate of 70,000 kilometers every second. If you looked at 2 points 10 gigaparsecs far apart from each other, then it's not 70,000, it's 700,000 kilometers per second, and so on and so forth. Because nothing can move faster than the speed of light, this puts a limit on how far away we can see or otherwise interact with things. If the amount of space between 2 points is growing faster than the speed of light, then there's nothing we can do to ever communicate or interact with that point in space.
You could try sending a message to that point in space, but since it's traveling away from you faster than the speed of light, that message will never make it there.
We say this is a point behind our cosmological horizon. So the size of the cosmological horizon, today it's pretty big. It's about 13.4 gigaparsecs away from us, or about 44 billion light years. But this horizon was different in the past. It was different because the universe was expanding faster in the past because it had a higher density.
All right, so there's a chance that has given you pause. We normally talk about the universe's expansion accelerating today, meaning that it was slower in the past and will be faster in the future. It's true that the expansion of space is accelerating today, but it was actually expanding much, much faster right after the Big Bang. What's really happening here is that the expansion of space depends on the density of the matter and energy inside of it.
So today, we are a pretty big dilute universe, and that drives expansion to happen at a rate of 70,000 kilometers per gigaparsec. But in the early universe, when space was much smaller and the density was much higher, that space was expanding much faster than it is today. So that means, in turn, that the size of the cosmological horizon in the early universe was a lot smaller. So picture, again, that region in the early universe with a little more density than average. If this region is really big, it might even be bigger than the size of the cosmological horizon at that time. And then it won't be able to collapse because even gravity won't be able to communicate across its whole volume. It'll essentially just sit there frozen until the cosmological horizon grows to become big enough to encompass the whole region. It will only be around that time that it starts to collapse and start to oscillate and produce sound waves. And the really cool thing is that all of the regions of the same size will kind of start to do this at the same time in unison. So all these different regions spread across space kind of function as a choir, starting to generate the same note at the same time everywhere across space. And in different regions, maybe smaller regions, these things will oscillate faster and they'll start at a different time, an earlier time. And those will produce a different note starting in unison at a different time, and so on and so forth. So we have a bunch of different regions of different size, all kind of singing in unison in the early universe. It's downright poetic if you think about it.
Today's episode of Why This Universe is sponsored by the International Space Station. Every day, 250 miles above our planet, amazing research and technology development to benefit humanity takes place on board the International Space Station. From improving quality of life for cancer patients to one day manufacturing artificial tissue and organs in space, we're enabling a broad community of dreamers to solve some of the world's most pressing challenges. How can you begin your journey and gain access to this ultimate research and development environment? Attend the International Space Station Research and Development Conference in Seattle, July 31st through August 3rd. Learn how leaders in academia, industry, and government agencies are seeing the value in space-based research and development to advance fundamental science, technological innovation, and in-space manufacturing. This is your opportunity to network with trailblazers in the space community and hear firsthand from those who have already conducted research on station. Join the ISS National Laboratory this August in Seattle at the 12th Annual ISS Research and Development Conference. Visit issconference.org to register now. So far, this has all been a bit theoretical. We obviously didn't have a podcast team recording sound at the Big Bang, so it doesn't seem possible to collect that sound from the source. Or is it? Turns out physicists are very clever.
We can't actually hear the sound waves that the Big Bang produced, but we can see them in a sense. So 380,000 years after the Big Bang, the electrons, protons, and nuclei in our universe all combined to form electrically neutral atoms for the first time. And when that happened, the universe became transparent to light for the first time, producing what we call the cosmic microwave background. So when we look at the cosmic microwave background today, which we're all kind of bathing in this light from the Big Bang, we get a snapshot of all of the regions of over and under density in our universe 380,000 years after the Big Bang. When we study those kind of clumpy hot and cold spots on the map of the cosmic microwave background, we can kind of see a picture of all those pressure waves as they were at that moment in time. It's kind of like being able to look inside of an organ pipe mid-note and looking where all the atoms are and noticing there's high pressure here, low pressure here, high pressure here, and get a kind of instant snapshot of what kind of sound was propagating through that organ pipe at the time. So when we look at the CMB, we see a bunch of these hot and cold spots which correspond to these regions of high and low density. And these spots come in a bunch of different sizes. The most numerous of these spots are about a degree in extent. So they occupy a piece of the sky that's roughly as big as the size of the sun or moon or something like that. That's about a degree or so. And these 1 degree spots correspond to regions that were reaching a state of maximum compression for the first time around the time that these atoms were being formed 380,000 years after the Big Bang. So a normal sound wave that you can hear with your ear might be hundreds of hertz or, oscillate hundreds of times a second. This is a sound wave that oscillates 1/2 of a time in 380,000 years. So it's a really, really, really low frequency sound wave. I estimated this on my paper here that it's about 10 to the minus 13 hertz. And that's at the time of the Big Bang. Since then, the stuff has stretched, so it's even lower frequency. This is a deep, deep, deep hyper bass note. Way, way, way out of the range of human hearing.
Good luck finding something cooler than early universe hyperbass, by the way.
But then you see other higher frequency notes too, but these are all still way, way lower than the frequency of human hearing.
The music of the Big Bang might have been a super low rumbling hyperbass way out of the reach of our tiny human ears. But hope is not lost. If you want to get a sense of what this sounds like, you can shift the frequencies of these Big Bang sound waves way up to the human range. It's a huge shift, something like 80 octaves, but the result is a beautiful way to experience the beginnings of our universe as we know it. This shifted recording comes to us from physicist John G. Kramer from the University of Washington, who extracted the CMB data from the Planck Space Telescope and turned it into something we can hear. This clip represents sound from about 380,000 years of time soon after the Big Bang, compressed into about a minute. It's a bit intense, so feel free to skip it if you're sensitive to noises. So that was 380,000 years of cosmic music squeezed into about a minute and shifted up about 80 octaves. You may be wondering, is this all just a fun little side project? Or can we actually learn anything new from these studies of sound after the Big Bang? It turns out that we really have learned new things about our universe from this research. Here's how.
So just like most musical instruments, the early universe didn't make sound at just one frequency, but it made a bunch of different harmonics, okay? So if I pluck my guitar string, I get a superposition of a bunch of different standing waves or harmonics, and the Big Bang did the same thing. So we get the lowest frequency that corresponds to those sound waves where the 1 degree spots, which were reaching a state of maximum compression just as the CMB was forming. But there are also ones where from smaller regions that kind of compress and reach a maximum state of expansion at the time of the CMB. And there are other ones that compress, expand, compress by that time, or so on and so forth. So you have this evenly spaced set of harmonic frequencies, all of which we can see in the cosmic microwave background. So you get a whole series of harmonics or notes when we look at the CMB. So by studying these acoustic waves in the pattern of hot and cold spots in the CMB, cosmologists are able to learn a lot about our universe's early history, evolution, and composition. Since these hot and cold spots are the consequence of these sound waves, the sizes of these spots depend on things like the speed of sound or the speed that sound propagated at in the early universe. And I said before, even in our own air, that depends on things like the temperature and pressure at the time. So by studying the acoustic patterns in the CMB, we can measure the speed of sound in the early universe, which tells us about things like how many protons there were in space, because the more protons there were, the more they will affect the speed of sound at these early times. So by measuring these patterns of hot and cold spots, we measure how many protons there were. We can measure things like the total density or the total amount of matter in the early universe. We can measure things like how much dark energy is present in our universe. We can measure things like the large-scale geometry or curvature of our universe. All of these things we can extract from studying the CMB. I would argue, and I think it's a fair opinion, that if you took all of the data we have from all cosmological observations and put it together, the cosmic microwave background provides more information to us than all the other stuff put together. This detailed pattern, not only does it agree with our observations when we compare the predictions of the theory with what we observe, but those detailed bumps and wiggles in the harmonic frequency spectrum, they allow us to measure all of these things about our universe, not just at that time, but in the intervening time too. So by listening to the early universe, we can learn a lot about how things played out in those first few 100,000 years.
Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.